Welcome everyone. In this video, we are going to discuss one of my favorite physics topics of all time, which is normal modes. So let me write the topic. Normal modes. And our discussion will be primarily based on an example that I will give. We will consider a problem which is an example of a normal modes problem. So let's say that we have a floor and two walls. So these are the walls. You have the floor at the bottom and then the other wall. And let's say that we have three springs and then two masses attached to those springs. We're assuming that there is no friction in the system and that all the spring constants are the same and they have the value K, and the masses are the same and they have the value M. Now, so if I just, let's say, that each spring has, let's say, natural length L. So when they're at length L, they're neither compressed nor stretched. And let's say I drew them like that at their natural length right now. So if I were to just place this system, if I were to just leave it there, it would do nothing, right? It would just chill there. Because the springs are neither stretched nor compressed, so they're not going to be pushing or pulling the masses. However, and obviously like this is cool, but I'm not interested in this, right? What I'm interested in is how would the masses move if I were to displace them from their equilibrium positions. So let's do that. Let's say this is the first mass and this is the second mass. And let's say that I displace the first one from its equilibrium a distance x1, and I displace the other one a distance x2. And let's say that to the right is positive and to the left is negative. Okay? And so the question is, basically, what the question I'm asking is, what are the equations of motions for these masses? How would they move? And so we can look at it and then we can say, well, let's use Newtonian mechanics. Let's consider the forces on these. And we're also assuming that the springs are Hookean springs. That is, they obey Hooke's law. That's the force is proportional to the displacement from the equilibrium position, from the natural length. So for the first mass then, we're going to have mx1 double dot, right? That's ma for the first mass. Then that equals the total force, the net force by Newton's second law. Obviously, there is no net force in the vertical. The normal force balances the gravitational pull. So in the horizontal then, well, the first, so if you consider the leftmost spring, it's going to be pulling the mass backwards, right, to the left. So that's a negative force according to our choice of coordinates. So that's minus kx1. Plus, there's going to be the other force. Now, let's say that we can just assume this, right? Let's say x2 was greater than x1. So let's say that the middle spring, it was stretched. And if it was stretched, it's going to want to pull the first mass towards itself, so to the right. So we have the plus here. And then we're going to multiply k with the total amount the middle spring was stretched, which is x2 minus x1. I reasoned this assuming that x2 was greater than x1, but you can reason it otherwise. You can say, well, what if x1 is greater than x2? In that case, the middle spring was compressed, so it's going to want to push the mass to the left, right? And so it would appear as a negative force according to our set of coordinates. And if you look at this expression, if x1 is greater than x2, then this quantity is negative and k is positive. So we have a force that is to the left. So no matter your reasoning, you get this expression. And well, this is basically, we can write it in a better way if we open up the parentheses. So it's going to be, let's see. So minus 2k x1, I believe, yes, and then plus kx2. Now for the second mass, if we consider the mx2 of mx2 double dot of that? Well, by Newton's third law, you can just know that this guy will appear, but it will be opposite in direction this time, so minus k x2 minus x1, or you can do a similar reasoning to figure that out. And then if you look at the rightmost spring, well, it's going to be, so it was stretched, it was compressed by x2, so it's going to want to push it back, which is left, so minus kx2, right? And if you write this one, then that's going to be, let me be sure, so kx1, I believe, is that true? Yes, kx1 minus 2kx2. Cool. And by just looking at them, like, they're a bit problematic. These aren't that bad because this is a very simple setup. Like, we have the same masses, we have the same springs. So we could solve these coupled, as they call it, coupled differential equations. But I will, even though, there are like decoupling ways, there are normal corners, I think what they call, and or you can just like look at it and figure out what you need to do. But I will present the foolproof way of doing it, let's say, which is the way I do it almost always, and that is the matrix method of solving it. For that, I will express these two equations of motion as a matrix equation. So on the left, we're going to have x1 double dot, x2 double dot equal to, we will have a coefficient matrix, let's say, and then that's going to be multiplying the position vector. And inside the coefficient matrix, of course, I will have divided by these m's on both sides, and then you can just check that. I can represent the two equations of motion we have above as follows. Km minus 2k over m, right? So that's that. And now we've written it. So how do we go about solving it? Well, we will solve it in the manner that we solve differential equations almost always, right? How do we solve differential equations? We almost always guess a solution and hope that it works. The good thing is, for most of the cases, we know what the guess should look like, okay? And this is this is the point where I want to talk about normal modes more specifically now. Normal modes, unlike that, you can find a better textbook definition of this. But to understand it, for understanding purposes, normal modes is when all parts of the system, so I will say all parts of the system move, sinusoidally. I don't want to write it wrong, so let's say move harmonically, all parts of the system move. So normal modes of a system is when all parts of the system move in harmonic motion, simple harmonic motion. I'll put simple as well, if you will, simple harmonic motion with a fixed phase relation, so fixed phase relation, with fixed phase relation. All this means is, if you just imagine this, right? If you displace the masses randomly, they might do crazy stuff. But if you displace both of them to the right, you can see them moving together, just swinging back and forth without changing the length of the middle middle spring, right? Just imagine that in your head. If you displace both masses in the same direction with the same amount, they will just oscillate back and forth together with the same frequency. And so that's the first normal mode. And the second normal mode is if you displace them equal amounts but in opposite directions, they will do an in and out motion. Okay? So there are two normal modes for this. And we will see this mathematically, by the way. I'm just reasoning it out. I'm reasoning this so that the guess I am about to make for solving the differential equation, systems of differential equation, will make sense to you. I can guess that as harmonic motion as possible. And I see that we have two second order differential equations. So that means that to describe x1 and x2, I just need two constants. There will be two constants that are determined by the initial conditions, probably the speed, initial speed and initial position, right? So what I'm trying to get at is I can try a harmonic solution. I can try a sinusoidal solution to these differential equations, hoping that it will work. And it will probably work, because if we get a solution to them, then that's fine. And then the final solution, the general solution, will just be a linear combination of the normal mode solutions, okay? So what I will do now with these is I will look for normal mode solutions that are hopefully going to solve it. I keep saying hopefully, but I know, they do solve it, okay? But you will see that in a minute as well. So to look for normal mode solutions, I will, well, there are multiple ways of doing this again, but I will complexify the problem. So I will write it as, I will define let's do it properly. So I will define a z double dot, which is z1 double dot, z2 double dot. Basically the equation we have above, but in a complexified, basically, right? z1, z2. And the relation between x and z is that x is the real part of z, right? So you can you can choose imaginary as well. I'm just choosing real. It doesn't really matter. So from there, I will now represent this as z with the vector sign, with the vector sign below. This is going to be M, let's say, a matrix, and then this is the z. Now I will try, this is the guessing part, I will try that z is equal to some constant and then e to the power of I omega t, right? In which case then z double dot would be minus omega squared, because I squared is minus 1, a e to the power of I omega t. And sorry for the poor notation, a here isn't just a constant, it's a constant vector, so a. Because I tend to use uppercase letters for matrices, I wanted to change to a lowercase a. So if I now substitute this, we will have minus omega squared a e to the power of I omega t equaling, the matrix, then z, which is this guy. Of course, we can simplify by e to the power of I omega t. The time dependence cancels out. E to the power of I omega t is non-zero. And then we have m plus omega squared, the identity matrix, then a equaling 0. Now, how do we solve this? For non-zero a, so for non-zero a, we want this equation to be non-invertible, because if it is invertible, I'm talking about this part. If this part is invertible, then you would invert it, and a would be equal to, let's say, this part is, let's say that part is k, the matrix k. A would just be k inverse times 0, the 0 vector. This is a vector, right? And then a would be 0. But we're looking for non-zero a, so we don't want this happening. So k should be non-invertible. And there's nothing wrong with a being 0. It just means, it just refers to the situation I was talking at the beginning of the video. We just left the system there, didn't displace anything, so all the masses are just staying there, and x1 is 0, and x2 is 0 for all time. But that's not really interesting. We're interested when they are non-zero, when they're changing with time. So for non-zero a, this K matrix should not be invertible, and from linear algebra we know that for K to be non-invertible, it needs to have a determinant that's equal to 0. So the determinant of m plus omega squared I should equal 0. And let's construct that matrix then. So minus 2km plus omega squared k over m minus 2k over m. No, sorry about that. Was it a k over m? Let me just check. Yes, so it was a k over m. K over m minus 2k over m plus omega squared. This is the matrix, right? And we need that its determinant is 0. And I mean, well, how do we take the determinant of a 2 by 2 matrix? You just multiply these and subtract the multiplication of those. So minus 2k over m plus omega squared should equal k over m squared. Which means minus 2km over omega squared is equal to either k over m or minus k over m. Right? And so from here then, and these are going to be different omega, so let's call them omega 1 and omega 2. So what is omega 1 going to be? Well, omega 1 is going to be 3k over m under the square root. And then omega 2 is going to be k over m under the square root. And I hope this one makes you say, aha, because what is k over m? Well, that's just if you had one mass, k and then m, and if it was just oscillating, right? This is going to be the frequency. But what did I say for the first normal mode that we could think of? I said, well, let's draw it here. I said, we displace them the same amount. Well, I don't know how to draw it, to be fair, but I hope you can imagine it in your head. So we displace both of them in the same direction, the same amount. So the middle guy does nothing. Its length is fixed during the oscillation. And each of the masses are just oscillating under the influence of one spring. This spring for this mass and this spring for this mass. So we get the exact same frequency we would have for a one spring and one mass system. So that's a good thing. I mean, that matches our intuition. And then the other one is when they're doing the in and out motion. But like, we haven't solved it yet, right? We have the frequencies. What about what now, basically, right? We want to now find the relative amplitudes, let's say, of how the masses are, how the displacements of the masses relate to each other when they're exhibiting one of the normal modes. And finding that isn't awfully difficult. I mean, we will just go back to the solution we had, right? So we guessed this was the solution, that was a trial, and we found omega, but the missing thing is what A is. And A is going to describe the amplitudes. And so if we just consider the equation as it was, so the equation was that minus 2km plus omega squared k over m minus 2k over m plus omega squared, right? And then you had x1 and x2 equal to 0. The question is, how do x1 and x2 relate to each other for each frequency? If you're looking at omega 1 initially, well, then we plug that in. So we have k over m, k over m, k over m, k over m, x1 and x2 equal to 0, which shows you that x1 is equal to minus x2. And that's what I was talking about. That's in and out motion. We displace them equal amounts, but in opposite directions. And what if we consider the other one, the one that we could intuitively see? So if you look at omega 2 now, we have, so this is now k over m. So we have a minus k over m, k over m, k over m, minus k over m, x1 and x2. These guys equal the 0 vector, which shows you that x1 is equal to x2. As we had discussed, they are displaced same amount in the same direction. So then, we have basically two different solutions. So, I mean, like, we've solved for z, right? But z was the general way. So z satisfies the complex version of the equation we have. So both its real part and its imaginary part satisfy the real counterparts. And the real counterpart is the x. So the fact that we've solved for z means that we've also solved for x, okay? And this is just to keep it, like, nice and tidy so that you don't need to worry about sines and cosines. So then we found that x could be, you know, like it could be some constant a, then 1 and minus 1, so they have opposite, so they're like in opposite directions. And I want to talk about z first, actually. Sorry for not being sure about which one to talk about first. Let's say, I mean, we solve for z, right? So let's keep it at z. And that's, so it could be like, this first one could be that it's I omega 1 t. And what is omega 1? It is right here, the square root of 3k over m. And we also found another one for z2, which is another constant and same type of displacement. And then that. And notice that here, a and b could be complex. If I want to return to x1 as a function of time and x2 as a function of time, which I will denote nicely as this, then it's just going to be a linear combination of both of these, because this equations that the system of differential equations we were dealing with was a linear differential system, and for a linear differential equation, the one solution, if you have two solutions, their sum is also a solution. I have a video about this in this channel that sort of talks about this. I will attach that to the descriptions part so you can have a look at it. Hopefully it makes sense to you, but this is a very standard result that is used all the time while solving differential equations. So I hope you're familiar with it or will be familiar with it. And if you have persisting questions, please let me know in the comment section. I can talk about this more in a future video. But basically the general solution is going to be a linear combination of the two of both of them. And we're going to be taking the real part of this. And we have e to the power of I something, right? And we know Euler's identity that e to the power of I theta is cosine of theta plus I sine of theta. So it's a linear combination of cosines and sines. So at the end of the day then, we will basically have, well, we will have a, okay, so how do I want to do this? Well, let's say, yeah, like this then. So we will have this, then cosine of omega 1 t. Of course, there might be a phase here, right, that I didn't consider because, well, I said this was complex. If I want to make it real, that puts a phase there. And when we use Euler's identity, then that puts the phase back there. And then plus, so that's the same line still, b 1 minus I. I mean, we can say, well, let's say cosine again, but could have said sine. Doesn't really matter because we have the phase. And notice this a and this a, they're not the same probably. So maybe I want to define the first ones as a primes and b primes and the last ones as a's and b's. But this is it basically. This is the general solution. And the nice thing and an important thing you need to realize is we have two second order differential equations and we need to have four constants that determine them in the initially, yeah, so two for each of them basically. Two for each of them, and this first one, well, you could determine maybe from the initial position or the initial, well, basic, okay. I'm making this way more complicated than it needs to sound. We have two second order differential equations, so we're going to have two constants associated with each of them, which means that we are going to have four constants, four unknowns in total, four unknowns. And those four unknowns will probably be determined by the initial, well, they will be determined by initial conditions, and probably you will be given the initial velocities and the initial positions of the systems. So then you can describe how the system evolves with time. Anyways, I hope this video was helpful. If you have any questions, please add them in the comment section. I hope to see you in another video. Until then, take care. I just realized I should have been more careful about the transition from here to here, I think. Okay, so I will just carry it out. I don't think I did it justice. So we had, okay, I'll just talk about it in one of them, right? So if you consider Z1 equaling this one, right? So a prime minus 1 e to the power of I omega 1 t. So what I tried to say was, a prime, well, that's a complex number. Can be complex, but I can make it real if I take out the phase. Now it's the real a, let's say. So maybe I do not do something else. Let's say with c. So this is real now. And I know that x1 is going to be the real part of z1. And so the real part of this, well, the first part, that's real. So c prime. And then the real part of this. As I was saying, this is Euler's identity, which I have a video where I prove this. You can access that from the cards right now and also from the descriptions part. And so if you just look there, which I've proved in this channel, then the real part of the e to the power of I theta term is just cosine of omega 1 t plus phi 1, the phase. Okay, so that's how you obtain this part. And then you can also do the same thing on this to get the other part. And since we are considering linear differential equations, two expressions that are solutions are also a solution when you add them. Okay, I felt like my explanation wasn't enough for this, so I hope this clears up any confusions.